Okay, the purpose of this video is to talk about plots of motion, something we haven't done yet. So you can see a plot here, and why should we care about this? Hold on a second. Give me a second. All right. Hopefully, I think that's recording there. Okay, got it. All right. Sorry about that. Whatever. Why should we care about this? Number one, in general, to be a fully functioning member of modern society, you should know how to understand plots. It's important even in just like a newspaper article or something you'll read online. Occasionally there will be plots. And so basically learning how to understand plots is good for your general understanding of the world around you. Other than that, it turns out you can actually get a feeling for a problem at a greater depth by looking at plots. So you can look at a bunch of equations that describe these lines, but sometimes it's easier to just look at a plot and say, oh, this thing started out at position -6, and then it moved up to position 8, and then it came back down to approximately position 4. And so this can give you kind of a feeling like, oh, it looks like it's curving a little bit here. So there might be some acceleration, and more on that in a minute. But that's the idea, is you can kind of visualize the motion once you get good at this. And that's something that's not as easy with an equation. So that said, I've got some bullet points here. I'm looking at page 31 in my book. So you might want to get page 31 out in your workbook, volume 1. So, and I'm looking at this in particular is just the XT graph. So I'm going to erase this for now, because I want to have some room to talk about all these things. So right now we're just looking at the XT plot in this particular one. One of the things we notice, a horizontal axis is time. So you're probably used to graphs that look like this in a math class, Y versus X. Well, now we have, okay, and so you probably know the title of this is Y versus X. It's always vertical axis versus horizontal axis. So these plots are sometimes called XT plots, or X versus T. All right. So we're looking at the vertical axis, which is X. Oh my gosh. So this is a little bit different. The vertical axis is position. Now we should be careful here. Time is a scalar, it's just how many seconds, it doesn't have a direction. Position does have a direction. There's an implied I hat on all X values. The idea here is negative numbers mean to the left, it's a negative I hat. So the initial position here is -6 I hat. All right. So now I've got to be careful. Every time you read a plot, we also need to look at the units. So that's how these are labeled here. In this case, this is millimeters. So that's our next tip. Any well-made plot should make clear what units are used if it's a quantity that has units. So here we can see time is in microseconds, X is in millimeters. So all those prefixes, if you forget in my class, they're going to be right there on the back at the bottom, or on your test equation sheet at the bottom. They should be in there. All right. Now, I guess I've already mentioned this. X initial is the vertical intercept. The vertical intercept, the intercept of the vertical axis is there. So that's how I got this number right here. All right. Here's where it gets kind of fun. You see, I think I want to do See if this green shows up. If you've seen this in calculus, maybe you know that velocity equals dx dt, where that's a vector. Well, the derivative is like the slope. Now we have to be careful. In our class, we're going to be dealing with xt plots, vt plots, and at plots. So I'm going to be clear here. The slope of your plot may not be velocity. The slope of an xt plot is velocity. So if you look at some spot like right here, let's compare these points right here and right here. We could get the rise over run, and that would be, help me out here. I guess you can't help me out. We're on Zoom, and I don't know. It's been a long, weird day, and it's that daylight savings time day, so I'm super spaced out. Whatever. In this case, the rise is what? 2, 4, 6, 8 millimeters. What's the run? So if I go from right here, this is, I can see this is a half a second. It looks like that's about 1 second. So the velocity during this stage right here is 8 millimeters per second. And notice it's positive. If we look at this one over here, the rise is, let's see, we go down to 4. It's about -4 millimeters. And the run is 1, 2 seconds. So it's -2 millimeters per second. All right. Oh, I should be careful. What did I screw up on all of those? What are the units of time? I'm a bad person. So really that should be per microsecond. And over here, we could do microsecond. This begs the question, could we write this a little bit better? Maybe we should. This would be 8 millimeters is times 10 to the -3 meters all over 10 to the -6 seconds. Notice that's going to give you, what is this? 8 kilometers per second, because that's 8,000. If you punch this in, and so notice this one here would then be millimeters per microsecond is -2 kilometers per second. That's what that number turns into. Moral of the story here, the size of the tick marks matters. Okay, you have to watch your graphs very, very carefully. Did these go by 1s? Did they go by 2s? Did they go by 5s? Did they go by 30s, 4s? What? So look carefully. So whenever you're making a graph, we see checking the units is important. I just screwed up. Also checking the size of your tick marks. Also getting the plus minus signs right. All right. What else do I want to say about this one? I'll mention concavity here. So this is, this is supposed to be kind of a curve here. I'm going to make it look a little bit prettier. Let's just say this here. The concavity, if you understand derivatives, that's great. If you don't, that's fine. I'll put it here just for those of you that do. You might know that the second derivative of position is acceleration. That's like the concavity. So all you really need to know for physics 110, concave up implies positive acceleration. Concave down, acceleration is negative. All right, so far so good. An interesting thing that happens here, and maybe should I mention this here? How about I squeeze this in here? You know what? I'm going to do this on a new whiteboard and I'll come back to this. Hold on. Let's do it this way. Come on. Come on, computer. There we go. Sometimes I'm going to use the word speeding up or slowing down. Now, it turns out a lot of times people think anytime your acceleration is negative, you should be slowing down. That's just not true. And imagine this. Is it possible you could take your car, put it in reverse, and slam on the gas and speed up backwards? You'd have a negative acceleration and your velocity would be getting more and more negative. You could speed up going backwards. So one of the things we have to watch out for, speed in these problems is the absolute value of the velocity number. And maybe I'll put it like this. So if I could get our example on the board here at the same time, maybe let's do that. Here we go. So here, the speed is 8 kilometers per second. Here, the speed is +2. So we got to be careful about speed, all right? Then there's velocity. The problem is, a lot of times in chapter 1, we're going to write both of these with the letter V, and there's an implied I hat. So you have to be careful. Sometimes it helps just to write the word. All right, so if we're talking about speed and velocity, a lot of times I'll ask you about speed and velocity in a question. You might just write the word for these types of problems so you don't get confused by the fact that they both look the same. See what I'm saying? All right. Now that said, anytime acceleration and velocity have, am I going to fit this on? Same sign, speeding up. Opposite signs, slowing down. So let's take a look at this particular one. Here, I see that this is concave up. The acceleration is greater than 0 here. So here I have a positive acceleration. Now look, the value is negative, but the slope is positive. So at this point, notice right here, I have a positive slope, which means positive velocity. Maybe this might be confusing you. This was from a bullet point earlier. I'm going to erase that. Okay. That was just from my commentary a minute ago. So in this particular graph, it's concave up right here. So it's accelerating upwards. It's positive accelerating. I should be careful. This is an X graph. So it's accelerating to the right. All right. Now look right here. I have a positive slope. If you have a positive slope, that means velocity is greater than 0. So maybe I'll put vectors on these just so you can see it. How about I call it like this? V sub x. That way you're okay with the implied I hat there. And I'll call this A sub x. So the idea is A sub x and V sub x are both positive numbers. And we know there's an implied I hat on these. In this case, it's speeding up. Now, here we have to be a little bit careful. I don't have any regions on this particular plot where it's concave down, but you could have every possible permutation. You could have acceleration be positive and velocity be negative. Opposite signs, you'd be slowing down. You could have acceleration be negative and velocity be negative. They would be the same sign. That's the case I talked about going in reverse and speeding up. So I hope that helps you understand what I mean by speeding up and slowing down. And then finally, as a visual for this, maybe we could, I've got a simulation set up. Hold on a second. Let me find it. There we go. Let's share screen. Hopefully you're looking at my screen right now and can see this. So I'm going to play this simulation and I want you to focus on kind of this top graph up here. That's hard to see. I want you to focus on this graph up here. We could talk about velocity plots in the next video. All right. So in this case, I'm going to play this animation now and watch what's happening. Oh, and by the way, this is very similar to the thing, except this has different units. In this particular simulation, let's point out the position is in meters and the time is down here in seconds. So I just want to point out the units are a little bit different, but the shape of the curve is the same. And if you watch this little guy up here, you can watch the animation and get a feeling for this. So I'll put a link to this simulation in the comments to the video. But for right now, let's clear out all these simulations and watch this. Again, watch this guy right here and see what's happening and see if this makes sense. So I'm going to play it, and I'm going to play it at slow motion here. So first, he's moving to the right. Velocity is positive. Slope is positive. At this point, the velocity steps up. He's going really fast. And then at this instant, he turns around and goes really slow. Notice the velocity is smaller and negative. So you can kind of get a feeling for what this guy is doing. And I don't know if you want to watch, if you're curious, I'll play this again and I'll just point this out. And then again, I'll put links to this in the comments of the video. I'm going to play this again and you can actually watch the numerical values. So ready, here it goes. Notice the velocity is getting bigger and bigger. The acceleration is 3. All of a sudden, the acceleration turns off at 2 seconds. The velocity stays constant. And all of a sudden, quickly, he turns around. He needed a large negative acceleration to turn around. That's for a negligible amount of time. Then we can see the velocity is negative. So that's a simulation showing what's going on here. Like I said, I'll put the comments in the video. That's the same graph we just looked at there, and hopefully that gives you a better feeling. If you get good at looking at these plots, if you get good at looking at this junk, hopefully you can kind of imagine what's going on and imagine that simulation without having to